Calculate the displacement and velocity at times of a half second, 1 second, 1.5, and 2 seconds for a ball thrown straight up with an initial velocity of 15 meters per second. Take the point of release to be y sub 0 or y naught equals 0. In order to find the displacement under accelerated motion, I'm going to write it in terms of y, is 1/2 at squared plus vi t. Since we're taking our y naught, our initial y position, to be 0, then we won't have to worry about actually subtracting to find out where it will be. On Earth, the acceleration due to gravity at or near the Earth's surface is approximately 9.81 meters per second squared. The negative tells you it's down. Our initial velocity is a positive 15 meters per second. And this is a 0.5, not a 5. So that's going to be 7.5. Now if we, and I'm going to double check my calculation, but a negative 1.2275. I'm going to carry the extra decimal values right now inside the calculation and worry about rounding at the end. So this gives me a value of 6.2725 meters. Since we're looking at 3 significant digits, 3 significant digits, and 3 significant digits, 6.27 meters. That's how high it is at a half second. To find the velocity, remember acceleration is equal to delta V over T, which is VF minus VI over T. So, negative 9.81 is equal to a VF, which is what we're looking at the half second mark, minus the initial, which is 15 meters per second, over a time of a half second. Negative 4.91 is equal to VF minus 15. If we add 15 to each side, that gives us a final velocity at a half second of 10.009 meters per second. 3 significant digits would be 10.1 meters per second. Because the acceleration due to gravity on the moon is about 1/6 of the Earth, we can say the acceleration on the moon is a negative 9.81 over 6, which is going to give us approximately, and close enough for our purposes here, a negative 1.64 meters per second squared. Now, if the object were thrown vertically on the moon with the exact same initial velocity as on the Earth, how long would it be in the air? Well, one of the ways to think about it is that when we're talking about acceleration and time, when a ball goes up, it goes up and at the very top has a velocity of 0, and then it comes back down. So we can think about the fact that you've got a linear relationship between the velocity and the time, and it's going to be as a constant. So if the acceleration has decreased by a factor of 6, then that means that the time has increased by a factor of 6. Alright, how high would it go? Well, if you think about what's happened with regard to acceleration and time, 1/2 at squared plus vi t, while our acceleration has gone down by a factor of 6, our time has gone up by a factor of 6, and since we're squaring it, okay, what happens? Well, if we have 1/2, I'm going to write this as g over 6. I'm going to write this as 6t squared plus vi times 6t. 1/2 g times 6 t squared plus 6t vit. Excuse me, 6 vit. So that's 1/2 gt squared plus vit all times 6. Well, this is the same thing as we had on the Earth for going up a given height. So it is going to be 6 times greater. So it's in the air 6 times as long, it goes up 6 times as high. Now I will say, of all the examples that I've got, this is one that is probably the most painful to visualize, or close to it. If you actually look at the YouTube videos, you'll see that Colonel Stapp is pretty well beat up when they unstrap him from the sled. So if you calculate his acceleration and then his deceleration, and then you express it in multiples of g. Now, this is 9.8, 9.81, either one's close enough. So, on accelerating, he goes from rest to a top speed of 282 meters per second in 5 seconds. So the acceleration is delta v over t, vf minus vi over t. For some reason I either messed up on writing my minus or didn't even try to. Alright, so we have a final speed of 282, we have an initial of 0, and we have a time of 5 seconds. So 282 divided by 5 gives me 56.4 meters per second squared. If I divide this by a 9.8, 9.81, I get it in terms of G, about 5.75 G. That's his acceleration, and then his deceleration, when he slows down, it's the same thing, except we switch the 0 and the 282. The time to slow down, on the other hand, dramatically decreases to 1.4 seconds. So that's 201.43 meters per second squared. And if we divide it by 9.8 or 9.81 to get it in terms of G, sorry, that's a negative, then we have 20.5 G. Oops. And it's a negative again. So as you can see, these are some pretty significant accelerations, especially the deceleration. 5 to 6 G's is not bad for a fighter pilot, but negative 20 G's is going to rough him up a bit. Now let's say we're talking about an airman who's falling and manages to survive. Okay, you have some individuals who maybe fell 6,000 meters, roughly 20,000 feet. That's a pretty good size fall. If we assume that the speed on impact was 54 meters per second, what was the deceleration if they covered 3 meters in that distance? The easiest approach on this one is actually going to be to use the linear combination. The Vf squared minus Vi squared is equal to 2a delta y in this case, because they are in fact going down. So the final speed if they stop is 0. The initial was 54 meters per second. We need to find the acceleration or the deceleration, and they covered 3 meters in doing so. Well, 54 squared is, there's a negative there, it's 2916 meters squared per second squared. 6a, if I divide each side by 6, it's a negative 486 meters per second squared is a. So that's a pretty good acceleration. If you put that in terms of g, that works out to be about a negative 49.5 g. Okay, so that's some significant acceleration or deceleration. The fact that they only ended up with a small amount of injuries, and small amount being non-life threatening, is pretty remarkable.